Something slightly different. I've featured smoke detectors before, and this time I'm going to feature a different type of detector. It's a heat detector. And this one is, incidentally, the battery is flat. You'll occasionally hear it chirp. Unfortunately, it was supplied with a flat battery. It's a first alert kitchen heat alarm, the only fire alarm you can fit in a kitchen, they say. Hush button and test button, the usual things. Interestingly, it says that it's interconnected with up to 12 alarms. I've looked at this when I opened it up to put the battery connector on, and it doesn't seem to have that function. It also says 50% of fires start in the kitchen. Excellent. So this is also useful, this type of detector, in theatres where you've got sort of hazy atmospheres. You can get the commercial version of this, well, the professional smoke detectors, the interconnected ones, that are better in a sort of theatre environment because you get the foggy atmospheres, and the foggy atmospheres can get picked up by ionization detectors and the optical detectors. But the way these ones work is they've got a thermistor. You can just see the little tiny thermistor in here, and it detects either a threshold when the temperature goes above a certain point, or it detects a sudden sharp increase in temperature, so it gets an early response. So I shall test this one. So I'm going to warn you in advance that this is about to peep. So I'm going to press the button. If you get headphones on, this is a good time to turn the volume down. It's not too loud, that's all right, because I get my hand over it. So that's the test function. Let's activate it with heat. Actually, before I do that, let's measure the resistance of this sensor. So let's disconnect the thing momentarily. And the sensor has a resistance. There probably is other circuitry in here, but let's say 0.7 megohms. So about 700k, what does it measure around the other way? If it's similar, that means it's more or less likely to have been influenced by other circuitry. Yeah, about 700k again. That suggests it's quite a high resistance thermistor there. That's unusually a high resistance for a thermistor. They're usually in the sort of range of 10 to 100k. So let's put these connectors back on. It'll peep again briefly. And let's test it. So I'm going to cup my hand over this to reduce the amount of noise. And I shall bring down the heat gun. And we shall blow some hot air past it. Let's just check the temperature. Let's see if I can not melt the plastic in the process. And see if we can actually... Okay. So that works. Let's press the mute button. Mute button works. No, the mute button is triggered. I noticed this before when I was trying this out. That when the thermistor has been heated up, even though you're pressing the mute button, because it's cooling down, the unit detects the rapid change as the heat goes down in the thermistor, as its resistance rises again. It seems to detect that as a sort of repeat trigger. The chip number in this, originally I was expecting it just to be based around things like op amps and threshold detectors. It's an A5367CAT. A5367CAT. I'm not sure if you're going to get that. I shall look up the data sheet on that and see what we can find. And I'll get the circuit board out of this. Let's take it to bits right now, in fact. So let's get that off. Can this thing unclip? How is this held in? Oh, I see how it's held in. Let's see if we can gently unclip this without breaking it. The risk of breaking it is quite high. I'll try and prise it from the top. There we go. I'll get the circuit board out by releasing... I'll have to cut a little tie wrap. They've got a strain relief tie wrap and the battery connector. They've got clips for the circuit board. Let's unclip the circuit board. Oh, I've just burst that clip, not to worry. Lots of clips around the circuit board, and of course this detector, the sounder should I say, is clipped in as well. I shall unclip that. Then we'll analyse the circuit board and see what they've done here to detect that, and we'll find out what that chip is. There we go. Well, there we almost were. They've actually, the cable is completely captive for the battery connector. It isn't now. Right. Oh, it's a very dark circuit board in the back. That's quite annoying. It's going to make it a bit harder to trace that out. Not to worry, I shall go and investigate and see if I can find these things. What's this little transistory thing? 2N7000. That's a MOSFET, isn't it? A little FET. Okay, rightio, I'm going to investigate this. The reverse engineering has been done. It's quite interesting. There's some weird circuitry here. I'll let you cast your eye across it and then you can actually base your judgment on what you see, because there's something that's just a bit odd. So it turns out this is a standard smoke detector chip. It's designed to work with ionization or even optical type detectors, but in this case it's being used with a thermistor. But this little transistor here is an interesting function in that. The back of the circuit board is just very, very dark. It was quite hard to trace out, particularly the negative connections, working out if they were actually connected onto the ground plane, because there are such thin, spidery tracks going off onto the ground plane. But it is reverse engineered. I can show you what each group of components is doing. This group of components here is doing the sounder, which is just off here. I can show you the schematic. Let's zoom down a bit. This is the data sheet for it. It's made by Allegro. If you actually search for A5367CAT, you don't find it. Just leave the cat bit off at the end and just look for A5367 if you want to see this data sheet, because that is the number that finds it. Ionization smoke detector with interconnect and timer. So here is the schematic, and I'll zoom down a little bit, not too much, and make sure it's in focus. Interesting things that are worth mentioning. The circuitry has a compensating circuitry around the detector, because it's an ionization detector works in quite an unusual way. If it has, basically speaking, a positive plate and a negative plate, and then it's got a little emitter of americium, which emits radiation and it ionizes the air inside here, and that effectively makes it conductive, and it acts like a resistor. And the more smoke and pollutant is in the air, the more that sort of blocks the transfer of the charge across. And as far as I can see, its resistance effectively rises with the level of smoke and contaminants in the air, which is interesting. In this case, they're using a thermistor instead of this in a bridge, as I'll show you in a moment, to do that. Other things worthy of note around here. So here's the sounder circuitry. It's got a few resistors. The values are more or less the same. It's got the 1.5 megohm feedback resistor. It's got 200k instead of the 220k. Little capacitor there. And the other odd thing that's not shown in the schematic is this diode here, which appears to be just being used in conjunction with this to suppress transients in some way. Let me work out where's that connected. That diode is connected. Let me just get this other drawn up from underneath. It's connected from the H1 to, where's the other connection? To the positive rail. So H1 pointing towards the positive rail, that's the equivalent of, where's H1? Horn 1. So it's basically going from here, the main sort of plate, it's going up to the positive rail. Wonder what that is. I guess it must be to do with switching transients or something. Don't know. Maybe it's just to make the other circuitry more stable, because it puts out a series of spikes from the flexion of the transducer. I'm not really sure. The test function for this thing, there's a couple of options for the test. One is simply to put a resistor across either side of this, and that effectively skews the reading that this gives. It emulates the smoke. But in this case, they're using the timer mode. They're also doubling it. They're kind of doing that, but they're also using the timer function. Now, the timer function is for the mute function that you get as an optional extra in some smoke detectors, that when you press it, if it's sounding, it will temporarily mute it. And the timer runs for a while, and then it comes back in after that sort of time delay. It's for, when you've burnt the toast and it's triggered it. In the case of the timer being used, the timer out connects via a resistor to the sensitivity input, and you can program the sensitivity of this thing, but when the timer is triggered, it changes the sensitivity. It just makes it less sensitive. It'll still go off, but you've kind of muted it. It's going to make it less sensitive. And that's kind of what they're doing here as well. Other things worth looking at, it's got the LED output, which is just a resistor and an LED, 470 ohms in the case of this one. That's the 470 ohm resistor going over to the LED here. And that's more or less it. So let's take a look at the other page of the data sheet, just in case there's anything worth looking at. I'd like to point out that this is not the temperature in my room at the moment. It's just cooling down. I had the temperature sensor with a thermocouple heat shrinked onto it just to actually see what temperature it triggered at, which was 55 degrees Celsius it triggered. Anything else worth looking at in here? The data is all online if you want to take a look at it. It's got a block diagram inside. It's quite a complex little chip, but it's quite an old-fashioned little chip as well. I guess ultimately, things haven't really had to change much. Lots of characteristics and stuff. Let's bring in the changes, the differences in the circuitry associated with this particular product. So what I've got here, I'll just actually move these other things out of the way so it doesn't skid about all over the place. What I've got is, this is the chip. I've omitted all the other stuff, it's just not sort of needed to be seen. We have a potential divider here based on this resistor, and then the temperature sensor. The temperature sensor is marked 474. I guess that means it's 470K. Typically, a NDC thermistor will be marked as its resistance at roughly 25 degrees Celsius. A very common value of that is 10,000 ohms, 10K at 25 degrees Celsius. A lot of the little eBay modules, the temperature sensor modules, use that type of thermistor. Then this diode here, I do not know what they're doing here. It's very odd. Initially I thought maybe it's a zener, or maybe it's for current regulation. So that's the little diode across this sounder. This is the diode here, it's bigger. And I thought, is it a zener? Not sure. I tried putting a current limited supply in series with it, gradually wound the voltage up. It did not cut in anywhere between 0 to the 9 volts that's coming from the battery. So I don't think it's a zener then. I wondered if it was a current regulating diode. So I monitored the current as I ramped the voltage up again. And as the voltage went up, the current did not. The leakage current, reverse leakage current, it started off in the sort of region of 1 microamp, and then it just gradually crept up as the voltage went up to about 7 microamps. So it's not really what I'd think is a current regulating diode. Very strange. I'm not sure what's going on here. I don't know if they're just using it for its reverse bias leakage. It's a very strange setup. But either way, when you trigger this, you can press the mute button. When you press the mute button, which also doubles up as the timer start, when you press the timer start, I think it basically bridges this to the 0 volt rail and then triggers it. So that's the test function, but it also starts the timer. That lets them use the double function of the button. Let me think here. So it triggers the timer, and when the timer comes on, the output of the timer here goes through this 3.3 megohm resistor to sensitivity, so it changes the sensitivity. And at the same time, it turns on the little FET, which is normally biased off with this 18 megohm resistor here. And that FET then bypasses mystery diode. I'll just put a question mark to that. I haven't a clue. I really should just lop that off the board and see if there's a number on it. There is vague markings on it. I'll do that. It's the best thing to do. Rather annoyingly, it's not going to be easy to desolder. They've done that thing where if this is the circuit board, instead of just putting the lead through and then soldering it like that, they've actually put the lead through and then bent it over an angle and then soldered over the top of it. That makes them very hard to remove. It's not the best way to solder things, but it's just, it does hint that this may have been manually manufactured. So this function here, that whatever this diode's doing, it's basically dropping, when this FET's turned on, it drops it down to the 0 volt rail and reduces the sensitivity. So this thing triggers at 55 degrees Celsius, resets at 50 degrees Celsius. When you press the mute button, why did I put 63? Oh, yes. It triggers at a resistance of about 63k, which is equivalent of about 10 degrees Celsius less sensitive. It's like goes up to about 65 degrees Celsius. And the trigger point is round about 100k from the resistor, so it's quite a change from its cold value. And that is about all I can really say about this. It's a bit strange. It all seems to be hinging around this, because otherwise it would be a very simple potential divider. I wonder if they're using this to try and compensate for gradual voltage drop from the battery. You can program the voltage that it triggers the warning that the low battery the battery's needing changed, basically. The function of that, let me just get the data sheet here. Where is it? There, it's pin 3 low voltage set, so you can use a resistor in that. Are they actually doing that in this one? Have they got anything on pin 3? They have a resistor position to positive, but they've not actually occupied it. It's empty. Okay, so that leaves the logical thing that I should have done before. I'm going to have to get the soldering iron on. I'm going to have to lift this component out and see if I can work out what it says in it. So I shall just pause while I do that. Oh my, that's a bit weird. It is a Zener. And the reason I didn't detect it was a Zener is because I thought, well, since it's a 9-volt supply, I clearly don't need to go above 9 volts because it's never going to actually start clamping the voltage down. And it turns out it's a 10-volt Zener, a 1-watt 10-volt Zener. So even given this huge resistance here, it's never really going to, the voltage would have to be higher than 10 volts, and it would have to be a fairly high current for it to actually clamp at 10 volts, because otherwise it just sort of drifts up. Oh, I don't get this. I really don't know why they've done that. The only thing that comes to mind is they're using its reverse leakage in some way to form part of a potential divider. That doesn't make sense. It's had me... Once I took it out and I tested it, I found the number, which is it's a 1N4740A. I'll just write that down. 1N4740A. Once I'd done that, because it just didn't make sense, I went back to the circuit board and just double checked all the connections, and I don't know, because that end of the resistor is just connected to the FET and that Zener diode, which is rated above the voltage of the supply rails. That's got me perplexed. If it had been a resistor, it would have actually made more sense. I really don't know why they've done that. There must have been some reason they've done it. Could it be the wrong component has been fitted, or is it just because there's some wily trick that someone knows about reverse leakage of Zeners that, under their Zenering voltage? That's very odd. I don't get that. But the gist is that this unit is quite simple. I tried seeing if it would respond to a sudden increase in temperature by putting a auxiliary resistor across the thermistor and then basically suddenly stepping it down to emulate a sudden drop in resistance due to increase in temperature. Every time it just purely triggered at a threshold point of the roughly about 55 degrees Celsius. So it just seems to be a threshold level that it triggers on, and that is about it. That's strange. But there we have it, a rate of, I can't call it a rate of rise temperature detector anymore because it doesn't seem to work like that. A fixed threshold heat detector that then sounds alarm, and I suppose the main advantage using the smoke detector type chip is it's got the alarm functionality, it's got the ability to communicate if they choose to add that function. Oh, there is one other extra feature. The circuit board has an area that is not populated down here, and in the back of it it's got these two pads just at the bottom here, and it says I/O. That must be for the, it's certainly from the pin that it's actually coming from. It is the, is that pin 2 it's shown as? Pin 2, yes, I/O. And it does appear to be the interconnect to the other sensors, but it's just not used. So they've actually got a chain of resistors and capacitors for ultra filtering on that, mainly, presumably, to stop it from being false triggered by RF interference from mobile phones and stuff like that, inducing current or mains capacitively coupled noise onto the wires that might cause false triggering of the chip to think that, another sensor had gone off somewhere on the network. But the network is very simple. All it does is it pulls an input to one leg. I think it takes it positive. Yes, one of the connections is the negative. I was going to turn this over and take a look at the bottom. That's not good. Yes, this connection is negative. All it does is that any detector on the line can actually take this one positive, and when it does that, the chips that haven't taken it positive can detect that, and they'll go into alarm mode, but not flash their LEDs. All they'll do is beep, just to show that it's not them who's actually triggered the alarm. So there we go. Interesting. It's what it is. It's got weird quirks, but it is a temperature alarm, and that's about it. One last little thing I'm going to add here. I'm going to heat this up with the heat gun from a distance, just so it heats up slowly. And it appears that just the act of unsoldering and resoldering that Zener diode has changed its response, because it was originally about 55 it tripped. And now it's more closer to about 60-ish. So it's changed it's only a few degrees, but it does seem to have had an effect. And previously it would have cut out again when it reached about 50. Takes a wee while to cool down here. So if you have any, just above that, if you have any ideas about that Zener diode being used like that, could you leave a comment in the comments area down below, because it's just something weird. It just is not something I've come across before used in that style, but interesting nonetheless.